So, okay. So I think last time we proved something about Jordan blocks. So, last time we showed that so we had these Jordan blocks, right? So we had Jordan blocks. So these were the things that looked like AA10, AAA, zeros everywhere, right? These matrices. So they look like some identity matrix times an element plus Jn, and then this is like the band above the diagonal with ones. Okay, and then we said that for Jordan blocks. So for Jordan blocks, A, we had that V of A was isomorphic to. So this is the module associated to the matrix. This is the F of T. So this polynomial ring. So this is all over. So this is again, F is any field, right? So we had that this thing was isomorphic to F of T modulo T minus A to the N. So this is like kind of like the simplest possible. So it's a cyclic module, right? It's generated by a single element, so it's an F of T module, and then it kind of has this very, very simple form, right? And it's kind of what you get when you have, I don't know, it's kind of like some sort of multiplicity issue with eigenvalues in the characteristic polynomial. I mean, of course, some of them can diagonalize, but this, when it doesn't diagonalize, it's this form of a matrix that you get. Okay, so the upshot was that so the point was, the upshot was that you know, for if F is an algebraically closed field, and A is a matrix, is any matrix, then this V of A looks like, you know, it comes in a bunch of blocks, right? It looks like F of T mod A1 of T direct sum F of T mod AM of T. And then for each of these blocks, these blocks break down further. Okay, so why am I calling these blocks? Well, each of these factors here correspond to a block in the matrix in its rational canonical form. Okay, so and I gotta say a little bit more about blocks. Okay. So I guess the presentation is not so not the most ideal. Not furthers. Okay, so you have these AIs of T. So these things become a product from J is equal to 1 up to, let's say, Ni of T minus, so let's say that they're monic, right? Yeah, T's to be monic. So monic means the top degree term is 1, right? So then these look like this, and then we need some name for the roots. I don't know, what could be the root? Rij? Cij? Eij. Okay, so this is by the fundamental theorem of algebra. Okay, this is because this is the fundamental theorem of algebra. Remember, so the fundamental theorem of algebra says that and so this is what uses that f is. So it says that you can factor polynomials, right, into this uses you can factor polynomials into these linear terms, these degree 1 terms over algebraically closed fields. Okay, and algebraically closed means that every polynomial with f coefficients has a solution in f. Okay, that's the definition of algebraically closed. Okay, and so what does this mean? So this means that each of the factors here, f of t mod ai of t, right, this breaks down into a direct sum of j is equal to 1 up to ni, so it has some number of factors. And here we have f of t modulo t minus cij to the eij, like this. Okay, so this is this part here uses the Chinese remainder theorem. Okay, so we took this polynomial here. It may not be irreducible, right? In particular, we know over an algebraically closed field, it's not going to be. So then it breaks up into these little factors here, and these things, and then from our theorem, these correspond to Jordan blocks. Okay, so over an algebraically closed field, right, any matrix can be brought into Jordan canonical form. So, which means that it looks like it's similar to, so the theorem is if F is algebraically closed, and M is, or let's say an A is a matrix, in n by n matrix with coefficients in F, then A is similar. So meaning that you can change basis, right, to a block diagonal matrix with Jordan blocks. Furthermore, the blocks are unique. The block decomposition is unique. Up to permutation of the blocks. This last step, the uniqueness, is just from the uniqueness of the elementary divisors. Oh. Okay, so this comes from elementary. Okay, so I know I'm jumping around. Jeremy, are you okay?
Yeah, good.
Okay. Were you able to get in?
No, I'm still just copying from the screen share.
Okay. Sorry. I'm like. Okay, does that make sense? Like how this works? So the basis so again, it all comes down to choosing an appropriate basis so the linear transformation looks correct. And the basis comes from, the isomorphism here. So the choice of basis. In the theorem comes from the isomorphisms. Okay, let's call them phi and psi I. Okay, so this is one isomorphism, psi I, and then this is another isomorphism, phi. So using this isomorphism and this isomorphism, it gives you this kind of like the basis that puts you in rational canonical form, and then it gives you the basis that puts you in Jordan canonical form there. Okay. So I just want to say a little bit about the block matrices, just to be completely clear about what block matrices are and what they're doing. Okay, so maybe we'll do this over here, kind of like an aside on block matrices. Okay, so block matrices are really like direct sums, right? So if okay, so if I don't know, let's say T1 and T2. Okay, if this is a linear transformation, let's say Ti. Are linear transformations for I is 1 and 2. Then we get a new transformation, T1 direct sum T2, from V1 direct sum V2 to V1 direct sum V2 is also a linear transformation. Okay, so and so what I want, so these are going to be two blocks. Okay, so if A1 is the matrix for T1 with respect to the basis, let's say V1 through Vn, and A2 is the matrix for T2 with respect to the basis, let's say W1 through Wm, then then A1 direct sum A2, which is this matrix, A1, excuse me, sorry. Then A1 block, and then these are zeros here, A2. So this is the matrix for T1 direct sum T2 with respect to the basis V1 through Vn, and then you have W1 through Wm. Okay, so does that make sense? Like, so what blocks are they're really kind of like dealing with two independent problems, right? So whenever you have a direct sum, you should think that direct sums are silly. They're stupid, right? So they're just kind of like doing two problems at the same time in parallel. And you can kind of just work with each component separately. So once you have two blocks, right, it makes your life a lot easier. So the upshot is the upshot of this is that, you know, so if I do you know, so V1 direct sum V2, T1 direct sum T2 is isomorphic to V1 T1 direct sum V2 T2 as f of t modules. So like their decompositions, their invariant factors, you have invariant factors for each piece. Okay, and that's all you need to worry about. Okay, so let me show you how quick, how to use this, right? So let's do an example. Okay, so consider the matrix. Let's call it C. C, not C. C is a bad letter. A. Okay, so this matrix A, let's do the matrix A1, 0, A. Okay, then we'll do B, 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 0, 0, 0, 1, 1, 0. Okay, we'll do it like this. All right. Then we have 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, so let's consider this matrix A. Okay. Okay, so this thing, what's the rational canonical form of this? Right? So the rational canonical form will be the product of the rational canonical forms, but we already know that this thing is already simple, right? So the rational canonical form. So okay, so first of all, the determinant is the determinant of the blocks, right? So for block diagonal matrices, so the determinant, the characteristic polynomial here is the product of the characteristic polynomials. Okay, so it's the product of the characteristic polynomials of the blocks. Okay. So that's something that you should check, is that for block diagonal matrices, when you take a determinant, it's the product of the determinants. Okay. So the rational canonical form of this, so we know what the rational canonical form of this one is and the rational canonical form of this one is, right? So we know so I guess it's so yeah, so that the rational canonical form forms of the blocks are C t minus a squared and C t minus b squared. Okay, this isn't quite in rational canonical form though, right? Because right, you have this divisibility condition, right? So you need one invariant factor to divide the other invariant factor. Okay, so So this means that V of A. Okay, so this is isomorphic to f of t mod t minus a squared, direct sum f of t, this is cubed, t minus b cubed. Okay, so so this is what we have, and so this thing is isomorphic to. So this is the Chinese remainder theorem in reverse. So now this is kind of an elementary divisor form. Let's do it like this. T minus a squared, t minus b cubed, like this. So this implies that the A has rational canonical form. So now this is in invariant factors. This is invariant factor form. Okay, and of course I'm supposing that A is not equal to B, right, this whole time. It has rational canonical form. The companion matrix of this mess. Okay, and then you can expand that out and figure out what the coefficients are, but I'm not going to do that. Okay, so this is the companion matrix, right? Of t minus a squared, t minus b cubed. Okay. All right. So that's pretty much all I wanted to say about this example. So there's some examples like this where you get blocks and you get to simplify things because you have blocks. And that's all I really wanted to say about the Jordan decomposition. Do you guys have any questions about that? It is true that you can like make this similar to these two blocks here, this block here and this block here, but that's not a rational canonical form just because of the divisibility condition, right? Because by definition, rational canonical form, you need the first invariant factor to divide the second invariant factor to divide the third, and so on and so forth, right? Okay. I will take the silence to mean that everybody is happy. Or they're going to come refer to this later. Okay, so we're going to switch topics now. So that was modules over PIDs, and I think we did that pretty thoroughly. All right. So I'm going to move into a different topic.